ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. This is your Captain Shreyas, your physics master teacher. We'll be going live soon, so quickly mark your attendance by smashing the like button.
Hello everyone. I hope I'm audible and visible to all of you. Do let me know quickly in the chat box if it is live, if I'm audible, if I'm visible. Yes, looks like it. I am so sorry because of some small issues. I was not able to come live. Extremely sorry. Sorry to keep you all waiting. But yes, now that I'm here, make sure that you call all your friends back to the session, because this is going to be a very important session with regards to the graphs. So the entire 12th standard graphs, there are many graphs throughout the 12th standard. That's what I intend to complete in today's session. Okay, it's a proper detailed session on graphs. Understand that. We'll revise all the graphs, we'll see all the graphs, we'll see the formulas if required with the graphs. Okay, but graphs is so important. You will definitely get many graphical based questions or to draw the graphs in your board exam as well as your other competitive examinations. Good evening everyone. Hi Avishkar, hello everyone. Hello Balaji, welcome Bala, welcome. Good evening Krishna, hello. Nice to see you back everyone. Thank you for liking the session and thank you for all your patience, and really means a lot. Yeah, you guys waited for me. I'm so sorry I could not join in before because of some studio issues. Okay, so let's begin with the class and we'll do chapter wise. Okay, and have you marked your attendance by smashing the like button? Do that right away right now. Yes, please do that right away right now. Smash the like button and yes, call your friends, mention in the group, in your Telegram, in your WhatsApp, whatever, that yes, Shreyas sir is live. Okay, so let's begin. Now we'll start with chapter number 1, electrical charges. I'm just going to make myself a little bit maybe smaller, not required for me to be so big, right? Okay, so we're going to start with electrical charges and fields, and then electric potential, capacitance, all these related graphs. Okay, so get ready for it. So let's start seeing graphs one by one. Now, before I begin, one small information for all of you with regards to graphs. Pay attention to this carefully, everyone. Whenever you have a quantity like, say for example, y, and I say it is proportional to x, then I know that the graph will be a straight line. But imagine, just one second. Yeah, but imagine a quantity y which is inversely proportional to x, then the graph will be something like this. This is basically hyperbola. This is basically a hyperbola. But when y is inversely proportional to x square, then the graph is still curved, but it is not a hyperbola. Please keep that in mind. The first case it was a straight line, second case it is a hyperbola, last case it is a curve, but it is not a hyperbola. And also remember, if y was proportional to x square, x is on the top, then the graph will be a parabola. Which bola? Parabola. Keep these things in mind. Because this will be useful for drawing the graphs in many chapters in 12th standard physics. Something which is very basic. Okay, so x is straight line, x square is parabola, 1 by x is hyperbola, 1 by x square is some curve looking like a hyperbola, but it is not a hyperbola. Okay, it's just a curve. Okay, now you will understand why we did this, because you will see so many graphs associated with this particular concept. Starting off with, when we write the Coulomb's force, the Coulomb's force is nothing but K Q1 Q2 divided by R square, or the electrical field as K Q divided by R square. If you notice over here, this quantity of force or this quantity of electric field, isn't it inversely proportional to r square? Isn't it inversely proportional to r square? So if it is inversely proportional to r square, my dear warriors, how will the graph look like? How will the graph look like? Think about it. How will the graph look like? It will be a curved line, but it will not be a hyperbola. It will be some curved line, but it will not be a hyperbola. Understood, my dear warriors? Very good. Very good. Very good. Keep this in mind. Awesome. Awesome. Yes. Perfect. Now, next important graph is when you talk about potential energy, the formula is K Q1 Q2 divided by R. If you talk for potential, it is K Q divided by R. Again, say potential or potential energy. It is inversely proportional to R. It is inversely proportional to R. So if one tries to draw the graph of potential or potential energy with respect to the distance, what kind of graph will it be? It will be a curve, but that curve will be which special curve? It will be a hyperbola. It will be a hyperbola. Understood? Everybody with me? Very good. So this was a normal curve. In the first case, this was some random curve. It is a curve, but it is not a hyperbola. In the next case, when it is inversely proportional to R, it came out to be a hyperbola. Very good. Congratulations. Now, next important graph which you must know. Next important graph which you must know, my dear warriors, is with regards to the field and potential inside a shell and outside a shell. When you take a shell, shell means it is hollow inside. There is no charge inside. Even if there is solid, the charges are only on the surface. So imagine a charged shell or a solid sphere where the charges only reside on the surface, and the radius of such a shell is capital R. And now there are two scenarios here. One is when you are inside, and the second is when you are outside. There are two scenarios over here. One is when you are inside and one is when you are outside. Bharat, this session might be 1.5 hours, 2 hours, 3 hours, depending on how much our time we take to complete all the graphs. We'll not think about the time for this, but it is going to be a long session. Okay. Now, observe this carefully, my dear warriors. When you are inside, that is, R is less than R, then the field formula is 0 and the potential formula is nothing but KQ by capital R. KQ by capital R. Similarly, when you are outside, basically outside, that is R more than equal to R, then the field formula becomes KQ divided by small r, and the potential, R square, KQ divided by small r square, and the potential formula becomes KQ divided by small r. So now let's try to actually draw the graph. Let's try to draw the graph of both the potential and the field. Both. So one is for potential, one is for field versus R. How will this graph look like? See, for field it is 0 till you are inside, and as soon as you go outside it becomes 1 by R square. So it will be 0. So nothing. It is flat. And then suddenly it jumps up and then it becomes a curved line over here. So where does that jump happen? That jump happens at R. And after that, you can see it is a curved line. Everybody with me? Understood or clear till this point? Yes or no? Very good. Yes, very good. Similarly, if you talk about potential, look at it. Potential is KQ by capital R. Now capital R means it is a constant, it has not changed. And outside it is kq by small r. Small r is a variable. So that means potential graph will be a straight line, till r. And once you go outside, it will be 1 by r proportional. So it will be like this. So it will become hyperbola. What an important graph. This is for shell, my dear audience. What is this for? This is for the shell. Very good. Next important graph. Let's go for it. Just like before, but this time this will be solid sphere, uniformly charged, uniformly charged sphere. That means the charges are not just there on the surface, but also inside. So this is your capital R. And there are two scenarios, my dear warriors. One is again when you are inside. And the second one is when you are outside. The problem happens only for inside. Outside is still simple only. If you talk about outside, that means R is more than or equal to R, then the field formula is still KQ divided by R square, and the potential formula is KQ divided by R. Yes. By the way, whatever I write today, you will be getting it as PDF. I'll be sharing the PDF, very soon. So stay tuned on the channel, stay subscribed, and be a part of the Telegram as well. Yes, I'll be giving it to you. So for now, you can completely pay attention and you can make running notes. No need to make fair notes. Don't worry, you will not lose any of these slides. I'm going to give it to you free of cost. Okay, I'm not going to charge you anything. All right, cool. So next thing, when you are inside, the field formula is KQ small r divided by r cube, and the potential formula is KQ divided by 2r cube, and here you have 3r square minus small r square. Okay, now is the tricky question. Let's see how many of you geniuses can figure out how these graphs look like. Maybe you can put it up in your running notes. I cannot see those running notes, but I will be very happy and proud if you are able to get this right. If you are able to get this right, I would be very happy. If you talk about field, when you are inside, can you see it is directly proportional to R? Can you see the field is directly proportional to R, my dear warriors? So that means it will be a straight line. Field will be a straight line. Yes. And the moment you are outside, then it is 1 by R square. So that means it will be some curved line like this. Wow, very good. So it is inversely proportional to R square outside, and it is directly proportional to R inside. Let's talk about potential. When you are inside, it is small r square. Small r square is there on the top. Potential proportional to small r square. That means it is a parabola. But because there is a minus sign, it is not an upward parabola. It is a downward parabola. It is not an upward parabola. It is a downward parabola. Those of you joined late, just some time back I told when it is x square, it is a parabola. I just told this. When x square is there on the top, so the variable is there on the top, it is a parabola, but it is a downward parabola. So directly proportional to minus r square. And then when you go outside, it is inversely proportional to r. That means it will be a graph like this. Inversely proportional to r. And this change happens at r. This change happens obviously at r. What a brilliant question, right? How many of you knew all these graphs before? Put a red heart. If you did not know this graph before, but you learned today how this works, Put a blue heart for me. Thank you so much. Thank you so much, guys. Yes. Okay. Next set of graphs coming up on your screen now. You should know how the field lines and potentials lines look like for different set of charges. Starting off with positive charges and negative charges separately. So here we take a unit positive charge, and here we take a unit negative charge. I can see a lot of blue hearts. I'm so glad there are blue hearts for the first time, because I'm happy that you learned this today so that in the exam you won't make any mistakes. Okay, so from a positive charge, we know that the electrical field lines, they go out. Electrical field lines, they go out. Perfect. And on a negative charge, the electrical field lines terminate something like this. They terminate something like this. These are the field lines. How will the potential lines, equipotential lines look like? How will the equipotential lines look like, my dear warriors? The equipotential lines look something like this. Circles, concentric circles, that's all. They just look like concentric circles. That's it. Same thing for a negative charge also. They just look like concentric circles. Concentric circles. I need to draw them. Concentric. Yes, that's it. So they are just concentric circles. Perfect. But this is simple. The main issue happens with dipoles and positive or opposite charges. That is something which you should be aware of. So if you have one positive charge and one negative charge over here, if you have one positive charge and one negative charge over here, then how do the field lines look like? Well, the field lines look something like this. From the positive, it directly goes to the negative. Earlier they were separate. Remember, one positive was far away from the other negative. Here both of them are close by. Then the field lines will be because of both of them, and they will start curving something like this. They will start curving something like this. Okay, so they will start curving something like this. So this is how the field lines look like when both positive and negative charges are kept together. When positive and negative charges are kept together. By the way, what is this system called as? What is this system called as, my dear warriors? When a equal positive and negative charge is placed together, what is it called as? That is basically called as a dipole. Exactly, it is just called as a dipole. This graph you should definitely know in case they ask you. Also remember few more things about this. This line on a dipole is called as the equator. This is called as the equator. And this line that you see over here, this is called as the axis of the dipole. This line, horizontal line, is called as the axis. The vertical line is called as the equator. Very good. Proud of all of you. Similarly, you will get over here just two positive charges, graphs also to be drawn. Just two positive charges, that's it. Then how will the field lines look like? Then they will repel from each other. They will not end anywhere because both are positive. They will start from the positive charges and they will go until infinity. They will go until infinity. Something like this. This is how the field lines look like. Look at this. Just look at this. Okay. So quite a lot of difference between the graphs before for a dipole and for two similar charges, positive, negative. This is how they look like. You should know how to draw all of them. Great. Next important graph with regards to electrostatics. Okay. With regards to electrostatics is for the torque or the energy, on a dipole. The torque on a dipole. The torque on a dipole. Remember, the formula for that is PE sine theta. And another graph you might be asked is the potential energy of a dipole. Potential energy of a dipole. The formula for that is minus PE cos theta. Minus PE cos theta. So how do these graphs look like? Let's have a look at it properly. Let's have a look at it properly. Some of you might have already guessed how they will look like. It's not that difficult to guess. It's not that difficult to guess. Yes, come on, my dear students. How will the torque graph look like? Torque has sine theta, so it will look like a normal sine curve. Exactly. So it will go from 0 to maximum and then come back to 0, right? And again, it will go back to negative maximum and again come back to 0. It will be a proper sine graph. Whereas if you talk for potential energy, it's a cos graph, but be little careful because it's a minus sign. So usual cos graph starts from positive value, then goes to negative value and then comes to positive. This will be opposite of that. This will be opposite of that. So it will go like this and then come like this and then go like this. So it starts from negative maximum, then goes to 0, then positive maximum, then comes to 0, then negative maximum. So that's the only difference. Otherwise, it is fine. Otherwise, it is fine. Okay, cool. Great, great. So you should know these graphs as well. Very good. Now, next graph, which you should know. Next graph which you should know. So we have done force, we have done field, we have done potential energy, we have done potential, we have even done torque and energy of dipoles, as well as field lines and equipotential lines of charges. These are some important things with regards to the standard electrostatics. Moving on now. Yeah. So moving on now to the next part. And yes, what is the next part? We have Gauss law. Gauss law already includes these geometries which I have just told you. The next important geometry which you might see probably in Gauss law is due to an infinitely long wire. How does the field vary? So due to an infinitely long wire which is charged. If you have an infinitely long wire which is charged and you are at some distance away from it and you measure the electric field, due to that the field formula is given by your K, then 2 times of lambda divided by R. What is this lambda? This is your charge per unit length. This is nothing but charge per unit length. So if you notice, field is inversely proportional to R. Field is inversely proportional to R. So naturally, if you draw the graph of field versus R, it will be just a simple rectangular hyperbola. It will be a rectangular hyperbola. This is how the graph looks like due to an infinitely long wire. Keep this in mind. It will be a rectangular hyperbola. If you talk about charge sheet, it is constant. If you talk about a charge sheet, I'll just mention it over here. Due to a charged sheet, it is basically the field is constant. Hence the field graph is a straight line, which is constant. So there is no fun in drawing that. There is no fun at all in drawing that. Okay, everybody fine till here? All right. So till now we have seen a lot of things with regards to electric charges and fields and electrostatic potential as well. Slowly let's go on to capacitance as well. Yes, coming on to your screen. Yep. Now One second. Yes, let me just keep on adding slides. Okay. If I ask you to draw a graph of the charge on the capacitor, versus the voltage, charge on the capacitor versus the voltage, how will that graph look like? Think about it. Charge on the capacitor versus the voltage, charge on the capacitor versus the voltage. That graph will be simply put a straight line. It will be just a straight line because Q is equal to CV. In fact, Q by V is C. Q by V is C, and Q by V is also the slope of the graph. So the slope of this graph will also give you the capacitance. Will also give you nothing but the capacitance. Keep this in mind. Okay, so charge versus voltage will definitely just simply give you the capacitance. Q is equal to CV. Very good. Very good. Yes, awesome. Yeah, tomorrow we'll be having the morning class. Yes, don't worry about it. Next, moving on to the next one coming up on your screen. How does the energy stored in a capacitor vary? Energy in a capacitor. How will that graph look like? Well, say for example, I draw energy versus the charge graph. Remember, the formula is half Q square by C. Q square, U is proportional to Q square. That means it will be a parabola. Exactly, parabola. It will be nothing but a parabola. Yes, derivations also I'll be giving it to you. Don't worry about it. But if you draw a similar graph for, let's say, potential energy versus voltage. Potential energy, but with regards to voltage, U is equal to half C V square. It is again proportional to V square. So this graph will also be a parabola. Keep this in mind. Yeah. Awesome. Perfect. For derivations, I'll be making a special video for all of you. Don't worry about it. Yeah. I'll be making a very, very special video. Yeah. Next, let's move on to the next. Yes. In capacitance. Yeah. Okay. You might be asked graphical based questions or just ratio proportionality based questions for parallel plate capacitor. Like, for example, capacitance of a parallel plate capacitor is epsilon naught A by D. So this is for a parallel plate capacitor. These kind of questions are very, very common, where area is doubled, how much will the capacitance become? Or the distance is doubled, how much will the capacitance become? And so on and so forth. So if you talk about capacitance with respect to area, because it is in the numerator, it will be directly proportional. But if you talk about capacitance with respect to the distance, it is going to be inversely proportional. That's the difference. Standard questions do come on it. Very, very commonly asked. Okay, again. Moving on to the next one. Yes. In capacitors, apart from energy, apart from the energy graphs, and apart from the this concept of parallel plate capacitor, area being increased or distance being decreased, and those things, other than that, you do not have many graphs over here. But sometimes you might be asked questions like, what happens when a dielectric material is placed, and how will the capacitance increase and all of that. So if those kind of questions come, then what you do is basically remember one simple fact. K, the dielectric constant just comes on the top. So more the dielectric constant, more is the capacitance. As simple as that. It is just directly proportional to it. Okay. So I'm not just making it separate. Yeah. Just 1 second. Yes. 1 second. Okay. Cool. Now let's go on to the next thing. Let's go on to the next thing, my dear warriors. 1 second. So sorry. Just need to arrange my chats. Okay, fine. Just a minute. Yeah. Rosna, tomorrow I'll be making a separate video on the entire physics marathon. So that time you please attend it. So at least you will gain some knowledge. Okay. So please watch that particular marathon. Okay, cool. Now, after this, let's go on to current electricity. Let's go on to current electricity graphs. These were the major graphs, right? Which are there in basically electrostatics. So now, why is this not visible? Is my iPad screen visible, guys? What just happened? What just happened? Why is it not visible? Just check this. Okay. Now is it visible? My screen, just check it. Now is it visible? Now is it visible? Just check it. Yes. Now is it visible? Okay. Perfect. Okay, cool. Let's move on now to current electricity. One of the major graphs which is there in current electricity, if you open up NCERT also, you will see one of the first few graphs that you will be needing is the Ohm's law graph. So let me talk a little bit more about that as well. So in Ohm's law, the main graph is of the voltage versus the current, and we know that the voltage is directly proportional to the current. But this is only true for some devices called as the ohmic devices only, like resistors. And most of the conductors, you will see the graph is a perfect straight line. But there are many devices where the graph could be curved like this or could be curved like this. Doesn't matter. So these are non-ohmic devices. The best example for that is a semiconductor. In a semiconductor, the voltage is not proportional to the current. Yes, it is not proportional to the current. Keep that in mind. They are having some curved graphs. So that is a non-ohmic device where voltage is not proportional to the current. Keep this in mind. Very good. Yeah, that is what is also there in your NCERT. Okay. Then another graph which you should also know is of the resistance graph, because V is equal to IR gives me the definition of resistance. How much is the resistance? How does resistance depend on different things like length, area, temperature? Resistance graph with variations of length and area, and resistance graph for variations with temperature. So let's have a look at both. Resistance with variation of temperature and resistance with variations of length and area. So when you talk about length and area, it is very, very straightforward. If you talk about length and area, it is very, very straightforward. So for example, if you take length, you can see resistance is directly proportional to the length. Bigger the length, more is the resistance. So it is directly proportional to the length. So resistance is directly proportional to the length. But when you talk about area, it is inversely proportional to the area. So the graph will be a curved line like this. So resistance will be inversely proportional to the area. Okay, so this is with regards to the length and the area. Then we'll talk about the temperature. When you change the temperature, the resistance also changes. So if you plot the graph of resistance with respect to the temperature, the graph will look like this, will look something, let's say, like this. But this is only true for conductors. For semiconductors, the graph will be like this. It is downwards. Meaning when you increase the temperature, the resistance decreases. So they have negative alpha, negative coefficient of thermal resistance. Whereas conductors, when you increase the temperature, the resistance increases. So they have positive values of alpha. So the graph's slopes only are different. For conductors, it is positive. For semiconductors, it is negative. But having said that, also bear this in mind. Second, that these graphs are only valid for small temperature range. This is only valid for small temperature range. It might happen that if you take a large change of temperature or too many temperatures you are taking for a very, very huge range, then you will most likely see that the graph will be a curved line. It could be a curved line like this, doesn't matter. It is only straight line for a small range. You can see it's curved, but not curved so great also. So if you take a small range, then you will see almost for this particular range, it is almost like a straight line. Understood? So this is something which you should keep in mind. So I'll mention it here. For large range, it is non-linear. It is linear only for a very, very small range. Keep this also in mind, my dear students. Very good. Excellent. Great. Shall we go ahead, my dear students? Everybody with me? Okay. Perfecto. Now, you might also get questions. With regards to, your drift speed and their variations with respect to other quantities. Like, for example, you might get drift speed variation with the relaxation time. The formula for drift speed variation with relaxation time is E by M into tau. This is how it looks like. Or sometimes you might be given drift speed in terms of some other quantities like current. And the formula goes like this of relation of drift speed with respect to current. Current is N VD EA. So if the graph is asked for drift speeds variation with respect to relaxation time, it will be a straight line, because you can see direct linear relationship, time is on the top. But if they ask you, how does the drift speed vary with respect to the current, then again you can see current is on the top, drift speed is also on the top, so again it is directly proportional to it. So it will be just a straight line. Ramesh Sankar, I'll be returning to Bangalore very soon, so after that I'll be getting my port back. So right now I'm not in my original home studio in my city, Bangalore, Nama Bangalore. So I'll be back soon and then I'll get back my mode. Okay, fine. Shall we go ahead? Very good. Next graph is for EMF. Very, very important graph of EMF. These questions have also come in many competitive exams many times. EMF, but what they give you is current on one axis, and terminal voltage on the other axis. Terminal voltage on the other axis. Now, how does this graph look like? Anybody knows this graph? Yeah, don't worry, it doesn't matter whether it is studio or not. In gaining the knowledge is very, very important. Anybody remembers how this graph of terminal voltage will look like? Yes, come on, think about it. Now, I'll give you a hint. There are two scenarios over here. One is when the cell is shorted, and another is when the cell is basically open. So there are two variations over here. There are two variations which happen over here. So when you basically keep the cell open, when the cell is open, then the current is not there. Open means nothing is connected. And the terminal voltage happens to be the EMF. But when it is completely closed, okay, then what will happen? My dear warriors, when it is completely closed? Think about it. The current will be maximum. In fact, that current will be just the EMF by R. That will be the maximum current that you will get. And the terminal voltage in general is E minus IR. In general will be E minus IR. This is the EMF. IR is the voltage drop due to internal resistance. So this is the drop due to internal resistance. If you notice, voltage and current, it's looking like a straight line. Equation. Yes, with a negative slope. So, yep, you're going to see a straight graph like this. It will be, it will not be a curve. It will be a negative slope. And notice how these things work. Okay, check out some special pointers over here. This point refers to maximum current, okay, and this point refers to no current. But maximum terminal voltage. So this point over here refers to no current but maximum voltage. That means it is open circuit right over here. This is open circuit, and this point over here refers to the closed circuit. So these are the two special points on that particular graph. A lot of people do not know about this. Trust me. Many people I have seen that they do not know this particular graph with regards to EMF. Cool. Let's go ahead. All right. So we're seeing EMF also. Yeah, apart from that, which other graph is there? Resistance is also done. Wheatstones does not have any graph. Neither does equivalent resistance have any graph. Yeah, those things are not there. Okay. So cool. I think we can go to moving charges and magnetism related graphs. Everybody ready? Yeah. So guys, see this session, right, will cover all the graphs which you are required for all your competitive exams, including board exams, of course. And if you do all these graphs, 100% your complete revision will happen with regards to graphical part, so that tomorrow if any question comes with regards to the graphs, you have revised it thoroughly right over here. Cool. Chalo. Let's go to the next one. Let's go to the next one. Yeah. Moving charges and magnetism. Let me also open up my NCERT right over here and see if we can find some nice graphs. Yes, we have some beautiful graphs coming up on the screen. Okay. Chalo. I'll tell you. With regards to moving charges and magnetism, one of the first graphs that you must know is, if you have a coil carrying current, and there is some radius r of that coil, the current in that coil is I, then there will be some magnetic field at the center. There will be some magnetic field at the center, and the magnetic field lines look somewhat like this. So first of all, you should be able to draw those magnetic field lines, because that is a very, very important diagram for all of you. This is how the magnetic field lines look like. And this magnetic field formula is given by mu naught I by 2r. Because magnetic field is on the top, radius of the coil is below. Hence, if you draw the graph of magnetic field with the radius, you will see it will be a curved line. Bigger the coil, smaller the magnetic field. Smaller the coil, more the magnetic field. That is something which again you must be aware of. But when you take a long wire carrying current, then the magnetic field lines are circular. Something like this, right? The magnetic field lines are circular. These magnetic field lines at some distance small r is again given by mu naught I, but this time instead of 2r, it is 2 pi smaller. If you notice, magnetic field is on the top, r is below. So again, the graph will be a curved line. Again, the graph of magnetic field versus distance will be a simple curved line. In fact, this will be a hyperbola. Even this is a hyperbola because it is inversely proportional to r. So this is a hyperbola. Next graph which comes is when you have a thick long wire and you have to draw the magnetic field inside as well as outside. So imagine this to be a thick wire. And you have to find the magnetic field inside as well as outside. There will be magnetic field inside. There will be also magnetic field outside that particular wire. Let me just draw that for all of you. 1 second. Little bit crazy, but yes. Done. That's done. Okay. So when you are inside a wire carrying current, this is a wire which carries some current, and the wire has some thickness, so it will have some radius. And when you are inside, remember one thing, the magnetic field is proportional to r. But the moment you go outside, it is inversely proportional to r. So that's the reason why this graph resembles your electric field graph for a shell or solid sphere, basically. Electric field graph for a solid sphere. So inside it will be proportional to r. That means it will be a straight line. Outside it is inversely proportional to r. that means it will be a curved line, something like this. So this is the graph of the magnetic field of a thick wire inside versus outside. This is also there as your in-text question. This is also there as your in-text question. Yes. Sir, in resistance graph, we have to make R is equal to I square, length square by V rho. Okay, I'll come to that, Rahul. Thank you for pointing that point also out. Yes, definitely. I'll just come to that in a bit. Just give me a second. Okay, let me just complete this part as well. Next is, if you take a small element of wire, and this I have seen many students make many mistakes. If you take a small element which is carrying some current, okay, let us show this element is carrying some current, and you are at some distance from it, let's say R, and at this point you want to find the magnetic field. And how does magnetic field depend on distance? So many people remember that formula. Yes, sir, I remember the formula is mu naught by 4 pi I dl cross R divided by R cube. So many people think magnetic field, this particular magnetic field, is inversely proportional to cube of the R. But that is not correct. Magnetic field is not inversely proportional to the cube of R. Can you guess what is it proportional to? Can you guess what is it proportional to? Well, let me give you a hint. Actually speaking, this will be mu naught by 4 pi I. This is a cross product. So cross product means sine. So I dl R sine theta divided by R cube. So one of the R will get cancelled and this will become square. This will become square. So technically magnetic field is inversely proportional to R square. Keep that in mind. Inversely proportional to R square, right? So that is the reason why you will see the graph will just be some random curve. It's just inversely proportional to R square. It's a curve. It's not a hyperbole. It's not a hyperbole. Okay. Now, some of you are also asking, sir, in current electricity, can you tell us how will the resistivity graph look like? See, let me tell you, R is directly proportional to resistivity. So if resistance varies like this, even the resistivity will vary exactly the same way. So resistance or resistivity will have similar graphs. For a conductor, resistance and resistivity will have very similar graphs because both the resistance and the resistivity are directly proportional to each other. Is this point clear? Very good. Now, understand that when I wrote resistance is directly proportional to length, this means you have taken another wire of a longer length. It's not that I have pulled the wire and elongated it. So when those questions come, then the answer is slightly different. Be careful. What do I mean by that? See, here when I wrote R is rho L by A and I'm saying resistance is directly proportional to length, here I'm using different wires of different lengths or areas. I take a copper wire of 1 meter length. I take a copper wire of 2 meter length. I take a copper wire of 3 meter length. And for each wire, I plot the resistance or I see the resistance. I see more the length, more is the resistance. But if I take a wire of some meters and then I stretch it, then it will not be like this because area will also change accordingly. How many of you realize it? Area will also change accordingly. Yes, definitely. Area will also change accordingly. So be careful about it. So what happens is R will be rho L, but instead of by A, it will be, instead of by A, what I will do, I'll write it as volume by length. Why did I write volume by length? Because I know volume is area into length. So area will be volume by length. So I'll put it as volume by length over here. So this will become rho L square by V. So now if you see the resistance graph, for length, it will be a parabola. It will be a curved line. It will be a parabola because the same wire is elongated. Same wire is elongated or compressed. So area variations are considered. Okay. So understand this. The first graph, here you take one wire like this, you take another wire like this. Okay, you are taking different wires. You are just taking different wires of different cross sections and areas, and you are measuring the resistance. But in this particular scenario, if it is given the same wire is being pulled, then the area will automatically change. To conserve the total volume. If you elongate it, area will decrease. If you compress it, area will increase. But in the previous one, it's my choice. I can melt copper or iron or steel or aluminum into whatever length and area I want it to. Is that okay? So in the previous one, you see if there are the wire 1 was being brought by this student, wire 2 was brought by this student, or multiple experiments with different wires were conducted, or the same wire only was pulled and compressed. Accordingly, the formula will change. Usually the questions are on the same wire being pulled or being compressed. Usually, that is what I have seen. Okay, most of the questions are like that. Yeah. So tomorrow, Varalakshmi, we are going to have a 12th standard marathon. Tomorrow. Okay, clear? And some of you were also asking with regards to power, sir, is there any graph for power? Well, let me tell you, the graph for power is very straightforward. Oh, by the way, tell me, is power proportional to V square or is power proportional to I square? Is power directly proportional to resistance? Or is power directly or inversely proportional to resistance? How do you decide when to use what? Well, it depends on what is constant and what is not. Remember, P is equal to V squared by R, and then if resistance is constant somehow, only then power is proportional to V square. When is power proportional to I square? Using the formula P is I squared R. If again resistance is constant, then power is proportional to I square. Okay. Then when is power proportional to resistance? Again, power is I squared R formula. Somehow the current is kept constant. Then it is proportional to R. When is it inversely proportional to R square? When you use this formula, P is V square by R, but voltage is kept constant. Then power is inversely proportional to R. So you read the question, what is constant, what is not. Accordingly, things will change. Is that okay? Many people make mistakes. Will the graph of VD and A be same as VD and current? Well, we'll come to that as well. So if you go to the drift speed, and if you draw the graph versus area, then it will not be the same. Reason being, drift speed versus area graph won't be the same because when you shift area onto the other side, where will this area go? Area will go below, right? Where will this area go, my dear warriors? Area will go below, right? So what will happen? If area goes below? It will be inversely proportional. So that is the reason why the graph will look like this. So you have to see VD proportional to current, straight line. VD inversely proportional to area. So it is a curved line. Is that understood? Pakka? Done, dusted. Shall we go ahead? Okay, I'm going very slowly so that everybody can understand each and every single graph. Okay. Right. So we have done this also. This was your Biot-Savart's law. This was your Biot-Savart's law. Biot-Savart's law. Okay. This is also done. So next thing which is there in your NCRT is with regards to solenoids. We'll come to that also. Hmm. Okay. If you take a solenoid, okay, this is a solenoid. You should know this with regards to the magnetic field lines. Very, very important. Inside a long solenoid, the magnetic field lines are almost like parallel to each other. They are almost like parallel to each other. So magnetic field inside is almost a constant. There is no change in it. And the formula is mu naught small ni. So if you again draw a graph of magnetic field versus current or number of turns per unit length, this particular graph is just going to be a straight line graph. But remember one thing, these same magnetic field lines, by the time they come over here towards the end, they start spreading away from each other. What do they start? They start spreading away from each other. So because of this, you will see the magnetic field at the end will be slightly less. Magnetic field at the end will be slightly less. In fact, it is mu naught Ni divided by 2. It is slightly less at the ends. It is less at the ends. Keep this in mind. Next thing, if you go outside, completely outside, these magnetic field lines are very, very far away. Very, very far away. So magnetic field outside or basically far away, you will see because these magnetic field lines go, spread out everywhere, you will see hardly any field will be there. So the magnetic field outside will be almost like zero, a big fat zero. Keep these things also in mind. Yeah. What is the difference between solenoid and an inductor? An inductor is a solenoid is an inductor. So it's just an inductor is just any coil, need not be a solenoid. Even a toroid can be a solenoid, even a normal coil can be a solenoid, even a square loop can be a solenoid. Hello unknown who is progressing. Yes, white color is I think it should be visible. Okay, but fine, I'll just try to make sure I'll use light color. No problem. No problem. Okay, let's go ahead. Cool. Very nice. For a toroid, let's go over here. Yes. Toroid is nothing but a solenoid, but which is bent. Toroid is nothing but a solenoid, but which is bent in the form of a tube. Something like this. This is a toroid. For toroid, the graph or the diagram is very simple. Inside the toroid, the field is circular. The field is circular inside, and it is constant in magnitude. There is no change in that. But if you talk about the field outside, the magnetic field outside a toroid is negligible. Hardly any field is there outside. Keep this in mind. So outside a toroid, there is negligible field, but inside there is a lot of field. Yeah. In Femix, I have shown that graph of terminal voltage versus, resistance and all of that. You can see, just rewind back the session a little bit, you will be able to see it. Okay, just given toroid in competitive exams, maybe it might be needed, maybe some other boards might need it, so just for the sake of it I have just done it. Okay, no issues. Now if you talk about magnetic dipoles, I'm not going to do it again. Magnetic dipoles are exactly similar to electrical dipoles, so please refer the previous slides. Where did I do it? Just some time back. If you go back, oh, don't worry, you're going to get the entire PDF. I've just done these dipoles as well, electrical dipoles. So torque on a dipole, potential energy of a dipole. Okay, all these things we have done there. So magnetic dipoles behavior is very, very similar to that. So let's not waste our time over there. So that's why I mentioned it, just so that you know that, oh, we have done this, and you should not feel like, oh my God, did we skip this or what? Okay, moving on. Next is the, magnetic moment of a coil. Magnetic moment of coil. So if you take a coil like this, it has its own magnetic moment. And the formula for that, remember, is like you have NTA. And you have NTA releases all the notifications and everything. Very similar to NTA. NIA. Instead of T, you make it I, NIA. Yeah. So all the students who want derivations, how about this? I have made some videos on derivations. How about I upload those derivations instead of a live class? Are you okay with it? I'll give you all the derivations. Is that okay? Give me a thumbs up in the chat box. Then I can utilize that time for other sessions. I will have some question solving, high weightage, leaked paper, those kind of sessions. What say? Give me a thumbs up. I'm reading your chats. Hello, Ibal Tab. Yeah, Kanisha, I know it was deleted. It's okay. Yeah. Yes, perfect, my dear warriors. So because it is NIA, what will happen? If you draw a graph of magnetic moment versus number of turns, ideally the graph should be a straight line. That's what you would expect. Yes, it is. But this is only true if you have sufficient wire to improve the number of turns. Imagine you have a wire and only that wire you have to wind it. I can make one turn. If I make one turn, then the radius is very big. But if I make two turns, then the radius will be small. If I make many turns, 5-6 turns, won't the coil become small? Are you able to visualize this? Think about it. If you make only one turn, it will be like this, maybe. If you make two turns, maybe the coil will become smaller. Maybe the coil will become, oops, is there paste? There is paste. Okay, but yeah, point is, it will become something like this. N is equal to 2, N is equal to 1. Yeah, correct. And if you make 3 turns, it will become even smaller. So if the same wire is used, then I don't think I should use proportional to N. I don't think I should use proportional to L. So the length of the wire will be 2 pi r. Length of the wire will be 2 pi r into the number of turns. 2 pi r into the number of turns. That means R will be L divided by 2 pi n. What will area be? Area is pi r square. That means it will be pi L square by 4 pi square n square. 4 pi square n square. Correct? Very good. So what will area come out to be? Pi cancels. You will get L square divided by 4 pi n square. 4 pi n square. So if I substitute that over here, what should I get? If I substitute that over here, number of turns into current, and instead of area, I will put L square divided by 4 pi n square. One of the n here and one of the n over here got cancelled, and the magnetic moment will be inversely proportional to n. Inversely proportional to n. So what will I get, my dear students? The entire problem only changed. The entire problem only changed. Can you see that? Okay. Yeah. Yeah. Yes. For all the lectures, whatever derivations are required, we'll try to do that. Yes, definitely. Yes, my dear students, what will happen? It will be inversely proportional. So hence the graph will be something like this. Okay. So this is for the same wire. For the same wire, it is inversely proportional to n. But if you use different wires, then it is proportional to n for different wires. If you can have a longer wire with more turns, then it is proportional to n. Understood? There is two different scenarios over here. That's why I have discussed this in detail. Magnetic. Very good. Excellent. Then the next thing that you have is the force between two wires. Okay, this is also very commonly asked, the force between two wires. Let's have a look at it. The force between two wires. So if you talk about the force between two wires, carrying current. What is the formula? Quickly think and let me know in the chat box. Yes, it was mu naught I1, I2. In fact, it is force per unit length divided by 2B. Do you remember this formula, guys? Yes or no? Very good. You remember this formula? Yes. So this is the force acting between two wires. Force acting actually per unit length. Perfect. Now, many questions again can be asked over here as well. Like, how is the force changing with respect to the distance or with respect to the current and all of that? So if it is force with respect to distance, it is very obvious. Force is on the top, distance is below. So hence the graph will be inversely proportional. So it will be a hyperbola. Keep this in mind, because D is below, force is on the top. If it is with regards to the current, then it is on the top. So it will be directly proportional to the current. So if it is current, so it is directly proportional to the current. Keep this in mind. Very, very straightforward. Cool. Now you should also know that the forces are attractive for same directions and it is repulsive for opposite directions. So that is another thing which you should know with regards to forces between two wires carrying currents. Perfect. Next important thing, your MCG. What is MCG? Moving coil galvanometer. Very, very important. Yeah. I did not put 2. Oh, sorry. I missed that pi. So sorry guys, in the previous one, I missed one pi. Yeah, so please add that pi. Yeah, thank you so much for pointing it out. Good, you guys are paying attention. Now, for a moving coil galvanometer, you should know that the deflection of that moving coil galvanometer is directly proportional to the current, but there is also constant of proportionality. Constant of proportionality. So what is that constant of proportionality? Let's talk about it. So here you have theta, here you have NBA by K, and here you have current. So you can clearly see my deflection theta is directly proportional to the current. So hence the graph will be a straight line. In fact, the slope of this graph will be NBA divided by K. And this is called as the current sensitivity. This is also called as a current sensitivity. Current sensitivity. How do you remember this NBA by K? How do you remember this NBA by K? Remember NBA, football. Sorry, not football, basketball, right? NBA is basketball, like you have FIFA for football, you have a BCCI, you have ICC Cricket World Cup, right? All right, everybody. So similarly for basketball, what do you have? For basketball, you have NBA tournaments. Basketball. So basketball is NBA. And basketball is played with hands or with legs. Basketball is played with hands or with legs. Thank you so much, Napman. Yeah. Eyeball tab, it comes by derivation, that 2 pi. It comes by derivation. Okay, we'll probably have a look at it. Yes. You play it with hands, don't play it with legs. So, don't play it with legs. Don't play it with legs. So, with legs, you will only kick. So, basketball is played with hands, so it is on the top. And what you don't do is kick it, and kicking is done below. So, K for kick, and it is below. K for kick, and it is below. That's how you simply remember it. As simple as that. Basketball is played with hands, so it is on the top. What you don't do is kick it. Where do you kick? From below, your legs. So K is in the denominator. As simple as that. Okay? Easy peasy trick to remember it. Tomorrow is at 11 o'clock. My class is at 11 o'clock. Keep this in mind. Okay. Perfect. Perfect. Great. Then after moving coil galvanometer, you don't have much over here. Then you straight away go to magnetic materials and magnetic properties. Initially, again, magnetic dipole is there. There is nothing special out there. Okay. And most of the things are like deleted, like, all those parameters, basic definitions you should know. But still, I will do a few things which I feel might be asked in different ways. Okay. So I'll still go through that. One of the most crucial thing which you should remember with regards to electricity versus magnetism is that in case of electrostatics, electric field line starts and ends. There is a start and there is an end for an electric field line. But in case of magnetism, when you draw the graph of the magnetic field line, there is no start, there is no end. They are always in loops. So it's always in loops. So the field lines. So this is the difference in electricity and magnetism. One of the major difference. Next important thing which you should know in magnetic materials is the magnetic property of relative permeability. Relative permeability is the actual permeability of the medium upon the permeability of free space or vacuum, and that happens to be 1 plus the susceptibility. X stands for susceptibility. Keep this in mind. susceptibility, right? Keep these things in mind. You should know that this graph obviously of permeability relatively versus susceptibility will be 1 plus x. That means it will be something like this. So if this is your relative permeability, this is your susceptibility. In fact, the graph even extends before as well. So in fact, I should start like this. 1 second. Yeah, this will be correct. So this is relative permeability. This is susceptibility. Now, if you see this region where susceptibility is negative, but relative permeability is less than 1. Relative permeability is less than 1. This is actually -1. This region is for diamagnetic materials. What is this region for? Diamagnetic materials. This region from here till here, where the permeability is small positive value or susceptibility is very less, then it is a paramagnetic material. It is a paramagnetic material. When the permeability becomes high or susceptibility becomes high, after that it becomes a ferromagnetic material. It becomes a ferromagnetic material till the end. Understood this difference of relative permeability versus susceptibility graph? This is again very, very important. Okay, cool, awesome. Next over here is how temperature affects each of these materials. How temperature affects each of these materials. Susceptibility versus temperature. Susceptibility versus temperature. Susceptibility versus temperature. A very, very important graph. I'm just giving it to all of you. If it is a diamagnetic material, it is a straight line. If it is a diamagnetic material, it is a straight line, meaning it is not going to be affected no matter what you do. No matter what you do, you will see that it will not be affected. So that's why it is a straight line. For paramagnetic material, it is inversely proportional. So susceptibility is inversely proportional to temperature. Here it is just a constant. And for ferro, till a certain temperature, nothing happens. It remains ferro material. But there comes a critical temperature called as the Curie temperature. After Curie temperature, it becomes into paramagnetic material. So after that, the graph looks like this. Because for paramaterial, it is an inversely proportional graph. That's why it becomes inversely proportional like this. Yeah, is that okay, everyone, with me on this? Perfect. Will they give constant values in the exam? I doubt if they will give it for all the problems or even theory points or whatever. So, or at the start, some places they might not. So it's better to remember all the constants on the safer side. Don't expect only the values of constants from the examiner's point of view. Okay? Okay. Perfect. Moving on. What is Curie temperature? Curie temperature is that temperature. If you take a magnet, you might have seen on the fridge you put magnets, you heat it. It will lose its permanent magnetic property. It will become a temporary magnet. It is no longer a permanent magnet. It will lose its properties. That temperature where it loses its permanent magnetic properties is called as a Curie temperature. It becomes a paramagnetic. Paramagnetic is a temporary magnet. For some time it becomes a magnet, again it loses its properties. So that is a paramagnetic material. Very nice. Great. So these graphs are also clear with all of you. Awesome. Hysteresis is removed. So that's why I have removed it. I am not going to draw it. Okay. Hysteresis is removed. So that's why I'm not drawing it. Yeah. Cool. Slowly, let's go to, I think EMI also I have put up over here only. Yeah, electromagnetic induction. Yes. See, guys, with me, you are discussing so many graphs. Otherwise, you would have missed so many things here. Are you enjoying the session? Are you enjoying the session? Let me just take a water break. Have you smashed the like button or not already? No, yes, come on. If you have not smashed it, do that right away, right now, guys. What are you guys waiting for? Come on. Smash the like button right away, right now. Show your love and support here for the channel. Yes, your favorite English channel. Please do that. Thank you so much. Thank you so much. Do that. Cool. All right. Now, in EMI as such, okay, you don't have many graphs, but still, whatever graphs can be asked, probably asked, I'll just do that. Starting with your magnetic flux. Magnetic flux is BA cos theta. Magnetic flux is BA cos theta. So if one were to draw the graph of flux with respect to theta, this graph will be just like a cos graph. So it will look something like this, then like this, then like this, just like a cos graph. That's how you would expect it to be. And from this, you get the graph of the EMF generated by a coil which is rotating. A coil which is rotating. EMF generated by your rotating coil. Basically, it is an AC voltage. And the formula is B A omega N cos. No, it will become sine omega t. Where does this come from? It comes from Faraday's law. Basically, E is minus d phi by dt. So if you take the derivative of this, cos derivative will become minus sine, and another minus will make it positive. So that's how you get this BA omega N sine omega t. And because B is constant, A is constant, omega is constant, N is constant, only varying term is sine omega t. You will notice the graph looks something like this, like a sine graph. Yes, just like what we would expect it to be with respect to time. It will go up and come down. It will go up and come down, and it will repeat itself. This is one time period. This will be the maximum value. This will be the minimum value. The maximum value will be BA omega N, which is also the amplitude, or the peak EMF or the peak voltage. Peak EMF or the peak voltage, that is the maximum voltage that we are talking about. Exactly. Very good. So keep these things in mind. Great. Next thing is graphically in terms of graphs wise in this particular chapter. What you might probably else get is for solenoids, nothing more, nothing less, right? Solenoids. So there's formula you should know, the formula for self-induction of a solenoid. And then you also have mutual induction of concentric solenoids. So when you have mutual induction of concentric solenoids, the mutual induction formula looks something basically like this. Mu naught, number of turns per unit length in the first coil, number of turns per unit length in the second coil. Then you have area of the smaller coil. area of that smaller coil into basically your you notice done, N1 is done, N2 is done, area is also done, and then you have basically the length of the solenoid. The length of the solenoid. Similarly, if you talk about the self-induction, it is mu naught n square area of that coil and the length of the solenoid. So accordingly, you decide which graph you might need. Say for example, solenoid's self-induction graph is asked versus number of turns per unit length versus number of turns per unit length versus number of turns per unit length. Because it is n square, I know it will be a parabola. It is directly proportional to n square. If it is asked with regards to area, I know it is directly proportional to area. So it will be a straight line. So it will be directly proportional to area. As simple as that. Similarly, for mutual induction coefficient, if the graph is asked for either N1 or N2, it will be just a straight line because it is directly proportional to N1 or N2. It is directly proportional to N1 or N2. If it is asked again with regards to area, it is again directly just proportional to that. So directly proportional to area. If it is asked for length, what will you do? If you ask for length, what will you do? Well, for length, it is again directly proportional to the length. It is directly proportional to the length. It is just directly proportional to the length. So straight line. That's all. Yeah. Yes. Perfect. Small n is number of turns per unit length. Yes. So again, you will have to see in the problem whether the length is kept constant or the total turns is kept constant or different solenoids is being used of different turns per unit length. Accordingly, you will change whether it is directly or inversely proportional to either of the quantities. Sometimes they can just tell you the length of the wire is constant, only the windings have been changed. Number of windings have been changed. So accordingly, you will adjust it just like we did it for the previous questions. Is that okay? Understood? Oh, clear? Oh, can we go ahead? Oh, very good. Yeah. Diagram of of these inductors. So for self-inductance, you just take one simple solenoid. That's it. For mutual inductance, it is basically two solenoids, one inside the other. Two solenoids, one inside the other. That's all. That's how the diagrams look. N1, N2 are the number of turns per unit length for inner and the outer solenoids. That's all. Great. Yes. Don't use SL Aurora and all that for physics board examination. Not needed. Yeah. I hope in Femix this diagram is also clear. Yes. Sensitivity graph flash rider. I have done that just some time back. NBA by K. I don't know whether you were there. Just check that out. Okay. So I've just done it right over here. Yes, Preeta, we will be doing that. Yeah, just for the board exams, I'll need to concentrate on the boards for some days, and after that, we'll be back to our usual preparation. Don't worry about it. Alrighty. Cool. So that's with regards to EMI. There is no other major graph which I can see or I feel might be asked in this particular chapter. Okay, nothing else is there. Okay, let's go to basically the next one, alternating current, because after that we'll have electromagnetic waves and all of that. So let's go to alternating current. Here you might have some important major graphs which are very, very important, or even phasor diagrams. So let's talk about that. Okay, so let's do this. In alternating current, first important graph. If you have voltage or current versus time, and let's say the graph goes up and down like this, down and up like this, it completes one time period, First things first, you should know this point is called as the peak point or the peak voltage or the peak current. Sometimes it is also called I naught. Sometimes this is also called V naught. Next important thing which you should know is RMS value. RMS value. RMS value looks something like this. 1 second. Yeah, this is your RMS value. So either it is VRMS or if it is a current graph, it is IRMS. Remember, the RMS value is always the peak value divided by root 2 for sine or cosine graphs. This is how it is. If you talk about the average will be always 0. The average or the mean value will be a big fat 0. These are the few terminologies initially which you must know. Next important thing in AC. Let me just show this to you. The voltage and the current may not necessarily be in the same phase. Meaning same situation. When voltage becomes maximum, it's not necessary current also becomes maximum. When current is 0, need not be voltage becomes 0. So you might often see things like this. Imagine this is something like, imagine this is current graph, and here besides it I draw a voltage graph. Maybe it looks like this. You can see the maximum voltage line, maximum current line, they are both different. RMS values different. But what is same is the time periods, but they don't start at the same time. So clearly there is a phase difference between the two. And you represent them by a phasor diagram. See, this graph is versus time. If it is voltage, then it is voltage versus time. If it is current, then it is current versus time. This is with respect to time, with the time how they are changing. In phase diagram, it is with regards to the situation. What is the meaning of phase? Situation. I am in a sad phase of life. This phase of life for me is where I am not using my big board. I am missing my big board. I am using this screen right now. So that phase means situation. So here it looks something like this. In phasor diagram, if I show a current phasor, like this, the voltage phasor is behind it, maybe somewhere here, like this, and clearly there is a difference between these two. That is your delta phi or just phi, which is called as the phase difference. Keep this in mind. This is called as the phase difference. Please remember that whatever is the height of this current graph, let's say I call it as I naught, will be exactly the length of this arrow mark over here. So the length of this will be exactly I naught. Similarly, whatever is the length of this phasor of the voltage will be exactly the height of this sine graph. This will be V naught. Okay, these are some things which you should know. So if I represent current as I naught sine omega t, this omega, whatever I write over here, is also the angular speed of rotation. In this phasor diagram. phasor diagram. In a phasor diagram, always things are rotating. Things are rotating. It's like remembering SHM is the projection of circular motion. So this is that circular motion. This is the circular motion, and this is that oscillatory motion, up and down, up and down. Remember this from SHM. So phasor diagram is that uniform circular motion whose shadow, whose projection, whose component is that oscillatory or SHM motion. Yes, very good. Excellent. Okay, so keep all these things in mind. Now, how to draw this phasor diagram for inductive, capacitive, reactive circuit? So I'll explain this to you in a very, very simple manner, and you will never ever forget drawing this phasor diagram. Show two lines. The horizontal line is always for the current. Horizontal line is always for the current. Just 1 second. Okay, horizontal line is just for the current. Now let's talk about the voltages. For a resistor, the voltage and the current are in the same phase. So always voltage across the resistor is in line with the current. Now remember the phrase, love is above all. Love is above all. So voltage across the inductor is something like this. VL. Love is above all. So that's why it is on the top. Love is above all. Naturally, who is left? Who is left? Obviously, voltage across the capacitor. So VC is always below. VC, voltage across the capacitor, is always below. Now, these three vectors, if you add them, VR, VL, VC, then it looks something like this. You will be left with VR over here, and you will be left with another vector over here, which is VL minus VC. VL minus VC. VL is more, let's say VC is less, then VL minus VC is the leftover vector because both of them are opposite to each other. So you add them using triangle law, and what you get is this particular. What you get is this particular vector, which is the total voltage, which is basically the total voltage. So now you can see the total voltage and the current have some phase difference between them. Have some phase difference between them right over here. As simple as that. Clearo? Perfect. This is how you're going to draw the voltage phasor diagrams for a LCR AC circuit. Same kind of things you can also draw for even resistance, reactance, and impedance. What do I mean by that? Always start off with current in the horizontal direction. That's what I have been telling you. Current in the horizontal direction. Now remember, just like voltage across the resistor is in sync with no phase difference, same way the resistance is in sync with the current. Love is above all, so the resistance of an inductor is on the top. So XL, this is your inductor's resistance called as the inductive reactance, is on the top. You have XC below. Capacitor's resistance is called as the capacitive resistance or capacitive reactance. So if you add these resistances also vectorially, resistances below, XL, XC are opposite, so they will partially cancel. You are just left with one simple XL minus XC. Assuming XL is more, if XC is more, then XC minus XL. The resultant of these two, the resultant of resistance and reactance together, is denoted by the symbol Z, which is impedance. Exactly. And the same angle will be there over here also and here also. Keep this in mind. Yes, exactly. So impedance will be right over here. This is your impedance. Perfect. So these are the major phasor diagrams for LCR AC circuit. Okay. Is this diagrams, these graphs, phasor diagrams are clear? then we will move ahead to another diagram which you must know, and that is with regards to the resonance part. If you draw a graph of the AC frequency versus the current. This graph looks very nice. Something like this. I don't know whether it will come. Oops. No, it didn't come. It's like this. Oops. Something like this. You will see that it reaches a maximum value of current at a certain frequency. This is the max current. And this is when the omega equals 1 over root LC. This is when a resonance occurs. You should know this graph. You should definitely know this graph. Yeah. Pranav will be sharing it very soon. Don't worry about it. We'll be sharing it very soon. Okay. Yeah. This is the resonance graph which you must know. Okay. For LCR circuits. Another important graph which you must know is something called as the power triangle. Many people do not know this. So let me explain this to all of you. You draw a right angle triangle. And the hypotenuse, you call it VI. And then you mark an angle, call it as phi, which is the phase difference between voltage and current. So naturally, the base of the triangle will be VI cos phi. The height of the triangle will naturally become what, guys? It will become VI sin phi. VI sin phi. Okay. Now, what is VI cos phi? If you remember, this is the formula for the power. And this particular quantity right over here is your power factor. This is your power factor. So, this is basically your real power. This is called as your real power. This hypotenuse without cos phi, is called as apparent power. What is this called as? Apparent power. And this VI sin phi, which is neither real nor apparent, that is called as reactive power. Exactly. Very good. So this power triangle related questions might also come in your board examinations. How much is the reactive power? How much is the real power? Those kind of things. Okay, cool. So that is also done. Phasor diagram is also done. We have seen LCR circuits. Perfect. Great. These are the only things which you will need in this particular part. Great. Let's move on. To electromagnetic waves. Wow, we are already on to chapter 8. Guys, we are already on to chapter 8. Yes, correcto. So, you should feel extremely proud. You have already revised almost 7 chapters graphs. Now on to chapter 8. Graphs. Few more graphs over there. And that's it. You are done with the graphs. Again, next lecture tomorrow. Again, next lecture day after tomorrow. So in these 5 days, this 5 days challenge, you're going to complete a lot of stuff. And let me also tell you that if you want to sit and revise in our library with our teachers and ask doubts, you can do that as well, free of cost, at our Vedantu offline centers. If you are not aware of it, yeah, let me just show that to you as well. Many centers are there. Let me just bring it up on the screen. See, these are the places where Vedantu centers are there. Have a visit, right from north to south, from west to east. We are slowly spreading our wings gradually, and many students have started studying with us at these offline centers. So if you know someone and you are happy with Vedantu, you can definitely recommend them. But even then, If you don't have any friends or you feel that no sir, I need it for myself first, then please visit these centers free of cost. You can attend the offline classes which are going on. Yes, absolutely free of cost offline classes which are going on with regards to the backlog completion or basic doubts. If you have, many mentors are there who will help you understand many concepts. So please be a part of it at your nearest offline center. You can also take offline courses at 50% discount. Yes, with lots and lots of scholarship right from foundation to JE level. Okay, so visit your nearest offline center. If you are in your city which has this center, you should take full advantage of it. By the way, I was just in Pune center. Next center which I'm going to visit very soon, coming up, Hyderabad and Chennai. So all the students from Hyderabad and Chennai, rejoice, I'm coming there very, very soon. I'll be announcing it very, very soon. Yeah. Suchitra, maybe you can put it up on my Telegram channel group, right? We'll discuss that particular doubt. Yeah, because I don't want to break the flow now. Cool. Chalo, let's go to electromagnetic waves. In electromagnetic waves, what is the main graphs that you will need? One is obviously the diagram of the electromagnetic waves. That is the main thing which you will need. Apart from that, there is not much which you will need over here. But still, I will give you two additional graphs which is not there in NCERT but which might come. So what are those graphs? So let's talk about it. Starting off with, how does the electromagnetic wave look like? Well, if you show the electric field like this, then the magnetic field will be in a perpendicular plane, something like this. Try to visualize this a little bit. Okay, these are in two perpendicular planes. One is electric field, one is magnetic field. One is electric field, other one is magnetic field. And this is how light will move. Electric and magnetic fields. This is the direction of light. So the direction, electric field and magnetic field, all three are mutually perpendicular to each other. That's one diagram which you must know. Another diagram which you must know, or basically graph, is how the electrical energy density varies with electric field, given by the formula half epsilon naught E square, as well as magnetic energy density. Magnetic energy density is half P square by mu naught. In fact, in both the graphs, you will notice one common thing, that the field square is there. The square of the field is there. So, no matter which graph you take, for electric field or magnetic field, you will see that the graph will be a curved line and it will be a parabola. With regards to energy density. Keep these things in mind. Very good. Excellent. There can be one more thing which might be asked in electromagnetic waves, and that is the speed of light. Versus variation with dielectric material variation. How does the speed of light get affected because of the dielectric constant? Speed of light is c, dielectric constant is k. Well, the formula is 1 by root mu E. What is this mu? Permeability of the medium. What is this E? Permittivity of the medium. So, remember one thing. The permittivity of any medium is permittivity of vacuum into the dielectric constant. So, if you notice, speed of light is inversely proportional to root of k. Is inversely proportional to root of k. Hence, the graph will be just some random curve. It will be just a curve. That's all. It's going to be definitely a curved line. Is this very, very clear, my dear warriors? Akka? Understood? Yes. Great, great, great. Q factor, graph and all they won't do. They will just give you this thing. What do you say? Formula based questions. Yeah. Excited to see you too, Sagruti. Yeah. WW means Courier Pandu's whistle koduge. Exactly. Okay. In some places, hostels are present. Like if I remember in Hyderabad, Bangalore, and I think even in Chennai, I think hostel facilities or at least the contacts of hostels are given. So even if you're from a small town or village, and if you want to attend the classes in the major city, you are free to do so, and we'll provide you the contacts of the nearby hostels or the tie-ups which we have in the hostels. Okay. Telegram channel is Captain Shreyas. Just search for Captain Shreyas. You will definitely get it. That's the name of my Telegram channel. Cool. Next, let's go to wave optics. Let's go to wave optics, my dear warriors. Let's go to wave optics. So what and all graphs we have in wave optics? Let's open it up one by one. Okay. So in wave optics, the graphs that you might need. Yes, what are the graphs? Okay, here is one interesting graph which you might need. First one, how does the fringe width vary with different parameters? First of all, if you know the formula, it becomes very simple. Lambda d by small d is the formula. Lambda d by small d is the formula. So the variations look very simple, guys. It's not that difficult at all. This is fringe width. If you want the variation with respect to the wavelength, it will be directly proportional. It is directly proportional to the wavelength. If you talk about distance from the slits to the screen, that is also going to be directly proportional to capital D. If you look at small d, then it is going to be inversely proportional because it is there below. So it is inversely proportional to small d. Okay, that is one thing. Next thing is the intensity of the light. Next thing is the intensity of the light on the screen. How does the intensity vary? How does the intensity of light on the screen in Young's double slit experiment? This graph is usually drawn at 90 degrees like this. Usually you show intensity here and the distance on the y-axis or from the center on the screen is shown over here. And this graph looks somewhat like this. It's a little bit interesting like this. Okay, like that, like this. And it keeps going like this, then like this, like this. It keeps going up and down. Actually, left and right over here. That's it. That's how the graphs look like. It keeps going, maximum intensity, no intensity. So wherever it is maximum intensity, like this point, this point, this point, these are your bright fringes. These are your bright fringes. But if you see this point, or even this point, or even this point, these are your dark fringes. These are your dark fringes. How many of you realize this now? Okay. And what is the formula for this? What is the formula for this? The formula for this is I is equal to 4 I naught cos square del phi by 2. Cos square del phi by 2. So that is the formula which you must know. Keep this in mind. It's basically cos cos square graph. It's not a cos graph, it is a cos square graph. Okay, bear that in mind. Cos square graph. Cool. Next important graph in your wave optics. Let's go to the next important graph in wave optics, my dear warriors. Is. Yes, what do we have? What else do we have? You have, yes, Malu's law. Malu's law also. You can have Malu's law and Brewster's law. Malu's law and Brewster's law graphs. So remember, Malu's law is nothing but the intensity of the light after the polarization or after the polarizer is I naught cos square theta. So it will be a cos square graph. Intensity of light versus theta will be a cos square graph, and cos square graph will never be negative. Please remember, it's square. So it will be like this. It will be like this. And it becomes zero intensity at 90 degree. It becomes zero intensity at 90 degree, and it becomes maximum intensity when you are at zero or basically even at 180 degree, and it keeps on repeating itself. So 90 degree, 270 degree, nothing passes. At 0 degree and 180 degree, maximum light passes. With regards to Brewster's law, you should know the diagram which is there. So you have a medium over here and you have air over here, and you should know this particular diagram where unpolarized light will come. It will get reflected. It will get reflected, and it will also get refracted. It will also get refracted. This will also get refracted. And when these two are perpendicular to each other, then the reflected light becomes polarized. It becomes polarized. When reflected and refracted lights are perpendicular to each other, and it also happens that this particular angle that you see, if you take the tan of that angle, you will get the refractive index of that particular medium. You'll also get the refractive index of that particular medium. Keep these things in mind, my dear warriors. Yeah, very good. Now, when I showed you the intensity of light on screen due to a Young's double slit experiment, there is also another graph of intensity, but for a not double slit, single slit experiment. There is a small variation. The intensity for diffraction from single slit, from not double slit. Double slit is interference, single slit is diffraction. So from a single slit diffraction pattern, how is that graph going to be different? Here, if you draw the intensity graph with respect to the distance from the center on the screen, initially, yes, you will see some similarity, but later on you will start seeing the difference. Later on, you will see the maximum intensity is not as much as before. Maximum intensity is not as much as before. It is something like this. It is something like this. Notice the difference in this graph versus this graph. Can you see it? In case of YDSE, the maximum intensities have the same value. It's like same thing is getting repeated, but here the maximum intensity is maximum only at the center, but as you go up or down, the intensity keeps on reducing slowly, it fades out. So that's one major difference. In fact, if you see, there is a difference column in NCERT also between single slit and double slit. That is one of the major differences. Yeah, cool. Yeah, we are coming to ray optics. Hold on, we have not yet come to ray optics. This was wave optics for now. All right. So these are the major graphical based questions or graphs which are there in wave optics. Let's go to ray optics and optical instruments as well. Yes, a lot of diagrams, or I would say graphs, are there in ray optics as well. Let's have a look at it one by one, my dear students. First thing is your what do you say? Deviations. Now, a lot of students get confused between deviations, formulas. Deviation, first thing, for a mirror, the formula is 180 minus 2i. Second thing, for refraction. So first was reflection from a mirror. Second is refraction. The deviation is modulus I minus R. Third thing, for a prism, delta is I1 plus I2 minus A. These are three separate formulas. Many people think I can use anything anywhere or don't even realize when you commit a mistake. If angle of incidence is given for reflection mirror, use the first one. If light enters and refracts, deviation is asked, take the bigger angle, take the smaller angle, subtract the two, I minus R, you get the deviation. If it's a prism, I1 is incident angle, I2 is emergent angle, A is angle of prism. That's how you get the total deviation. Is that clear? Everybody understood? Okay. Now, majorly the graph is there for prism. So let's talk about it. Deviation in a prism. Deviation in prism. How does the graph look like? Well, the graph is almost symmetric. So if you draw the graph of deviation versus the angle of incidence, this is the angle of incidence. You will see that the graph looks like this, almost parabola, and there is a point when the deviation is minimum. And this happens when the angle of incidence equals the angle of emergence. Then the deviation is minimum. It is also found for most angles which are close enough to the minimum deviation. You will see the graph is symmetric. So if you go some units here, then you go exact same units on the other side, the graph is like symmetric, and you will also find the same amount of deviation. You'll also find the same amount of deviation on either sides. Okay. But it so happens that if you have a thin prism, so let's take deviation in thin prism. Then what happens? There is not much variation. In fact, the graph is almost like this. Be it any angle of incidence, the deviation values do not change much. Can you see that? No matter how much you change the angle of incidence, the deviation has not changed much. Hence, only in case of thin prism, deviation for most of the angles is approximately the minimum deviation. Only for thin prism. This is for normal prism. You will see that, it can have many values. Only for thin prism, it's almost similar. In fact, there is a formula also. It is A into mu minus 1. If you want the formula for minimum deviation for a normal prism, the formula comes from here. Mu is equal to sine of A plus delta minimum, the whole thing by 2, divided by sine of A by 2. If you know the refractive index, if you know the angle of prism, you can find the angle of minimum deviation. Cool. Shall we go ahead? Everybody clear? Revising a lot of stuff, I hope. Great. Very nice. Next thing, what you should know. Is this particular graph or variations for different angles of incidence from a dense medium to a rare medium. This is also going to be very, very useful, especially in theory. And this is a common concept which is asked, and that is the concept of total internal reflection. Total internal reflection. You should definitely be able to draw this. Like, if there is a small angle of incidence, then the light will come out on the other side. If there is a small angle of incidence, the light will definitely come out on the other side. It will get refracted. But that happens only till a certain extent where the angle of incidence reaches a critical value, and then the light which comes out is almost like 90 degree, almost like 90 degree to the normal. This is called as grazing the light is grazing to the surface. Graze means it's almost touching. And finally, when the angle of incidence is very large, then it will no longer come out. It will get totally internally reflected. When the angle of incidence is more than the critical angle, then it will get totally internally reflected. So it will follow the laws of reflection. It will not go on to the other side. It will come back into the same medium. Keep these things in mind. Right. Perfect. These are the major graphs which are there in ray optics. Other than that, it is purely formula based or diagram based questions will come. So we'll come to diagrams maybe in another class. Diagrams is not a part of today's lecture. We are mainly concentrating on graphical parts. Yes, perfect. Now, some students also ask, sir, is there a graph for V versus U and all of that? The answer is yes. We can also draw graphs for V and U and all of that for mirrors and lenses both. So let's say we talk about mirror. And the formula for mirrors is 1 by V plus 1 by U is equal to 1 by F. 1 by V plus 1 by U is basically 1 by F. Correct. Now, if I want to draw the graph of V versus U, what I need to take care of? What are the different aspects I need to consider? This is object distance. This is image distance. First of all, rearrange this formula to make it look a little bit good. That's all. Rearrange this formula to make it look a little bit good. So how do we rearrange that? Let's do this. See, I can write it as 1 by V is equal to 1 by F minus 1 by U. Taking LCM, it will be U minus F divided by FU. So therefore, V will be equal to FU divided by U minus F. Now, take some special situations. My dear warriors. What are the special situations? Like imagine the object distance. Imagine the object is kept close enough to the focal point. If the object is close enough to the focal point, then U will be tending towards the focal length. Object distance will be almost the focal length. So the denominator will become very small, 0. So 1 by 0 will become infinity. So V will become infinity. Correct. V will become infinity. That is one scenario. So object distance is F. Imagine focal length is positive. That means it's a convex mirror. Let's take it like this. Then image distance is infinity. Okay, that's number 1. Number 2, if object is at infinity, think about it. Where will the image be formed? Assuming it's a convex lens. Let's take the example of a convex, not lens, mirror. Let's take the example of a convex mirror. The mirror is convex. So that means the focal length will be positive. The image distance will be plus f, yes or no? The object is at infinity. The object is at infinity. Actually, it should be at minus infinity, not plus infinity. Think about it. Object is at minus infinity, taking into account the sign convention. The image will be formed at f. Image will be formed at f. Now, at least now we have got 2 points. We have got 2 points. So 1 point, because of this, we got it here. U is f. V is going to be infinity. V is going to be infinity. So I'll draw a line like this. Second, U is minus infinity. V is going to be f. V is going to be f. So I'll just draw a horizontal line like this. I'll just draw a horizontal line like this. This is going to pass through f. This is also going to pass through f. And the intersection of these two is 0. Origin. So now, my dear students, rest of the graph will be just simply put curved lines. Simply put curved lines. Now, where will those curve comes is very important. Imagine if the object distance is negative. If the object distance is negative, right? Then the image is going to, like, for example, minus infinity. If the object is at minus infinity, close enough to infinity, very far away, the image is going to be formed at the focal point. Image is going to be formed at the focal point. Okay, and focal point is positive. Great. So I think the graph will go somewhat like this. The graph will go somewhat like this. Curved lines like this. And then again, it will come from the top and go like this. So when object distance is negative, focal length is, the image distance is positive. Perfect. So if it is on this side over here, then on the right side of this dotted line, it will be on the top. Something like this. They are the curved lines. Got it? So main thing is to identify the two dotted lines, and then you will have two curved lines on the opposite sides. That's how the graph looks like. In case of a concave mirror, the only difference is this point will change. The focal point will be negative for a concave mirror. So these two dotted lines will come to the other side because the f point will change. The focal point will change. That's all. That's how you draw these graphs. That's how you draw these graphs, and these graphs have been asked many times in some competitive exams. Boards, it is little bit rare. Boards, it is little bit rare. Oh my God. Are you ready for dual nature, radiation, everyone, of matter, nuclei, atoms? Okay, chalo, let's do this. Okay, so what and all graphs are there in these chapters? Number one, photoelectric effect, lot of graphs are there. So let's talk about the graphs of photoelectric effect. But before that, for photons, do we have any graph? For photons, do we have any graph? Yes, we have. One is this particular graph of momentum versus wavelength. And the graph of momentum versus wavelength is one like this, because momentum is h by lambda. Momentum is h by lambda. In fact, we also have energy graph for photons, energy graph versus wavelength. The graph again is like this only, because the energy of a photon is hf, which is hc by lambda. So it is inversely proportional to the wavelength. It is inversely proportional to the wavelength. Is this clear? Everybody with me? Is this clear? Everybody with me? Very good, very good, very good. Awesome. Let's move on. Next, for dual nature, before going to photoelectric effect, let me just complete this part. For dual nature of matter, see, if you take the energy of a particle, not photon, like a proton you take, electron you take, neutron you take, these are matter masses. The energy depends on the velocity, it's kinetic energy. So this energy is basically kinetic energy. It is just half mv square. So it is directly dependent on the speed. So more the speed, more the energy. So it is directly proportional to the square of the speed. The energy of the particle is directly proportional to the square of the speed. Also, the de Broglie wavelength of such particles. How is it dependent on the speed? Well, lambda is h by momentum, and momentum is mass into velocity. So the de Broglie wavelength is inversely proportional to the velocity. Keep these things in mind. Great. Next. You might be also asked that a particle is accelerated through some potential difference. In those cases, the formula used will be half mass into v square, which is basically your kinetic energy, will come from the potential energy due to the acceleration. So that means it will be the charge q into delta v. So therefore, the speed square will be directly proportional to the voltage difference. So if somebody draws the graph of velocity versus voltage difference, this graph, because v square is proportional to delta v, you will see it will be a curved graph. It will be a curved graph because it is square proportional. It will be a parabola. Because square, because it is quadratic. So it will be a parabola. Keep this in mind. Okay? Clear, guys? So you will see these curved graphs for, particle which is accelerated, momentum is asked, sometimes kinetic energy is asked, sometimes speed is asked. So it depends. Okay. Now let's come to photoelectric effect, which also has many graphs. Photoelectric effect. One of the major graphs that you have is the graph of current versus intensity of the light. So you have the current versus the intensity of the light, and that graph is simply put a straight line. It is directly proportional. The current is directly proportional to the intensity. The photo current is directly dependent on the intensity of the light. What is the meaning of intensity? Intensity of any light is directly proportional to the number of photons. In that light. In that particular light. It is more intense, means the light is carrying a lot of photons, lot of energy. Yeah. I don't have a studio because I'm in Pune and I'll be back to Bangalore very soon, and then I'll be back in my studio in the big board. But I feel today's class is better on this iPad because drawing these graphs is much easier. I feel my diagrams will come much better on the iPad rather than on the board, because the board I'll be drawing in freehand. Okay, this is one of the first diagrams, guys, which you must know. Next diagram is of the current versus the voltage. Let's draw that. It's looking like this. Here you have the current, and here you have the voltage, How does this graph look like? Well, it's very interesting. Let's draw this. In fact, we have to draw it in the second quadrant also. It starts from a negative voltage value and it goes like this. And then it again goes like this. Why does it go like that? Well, I'll tell you. First of all, this point over here is minus Vs. That Vs stands for stopping potential. Stopping potential. Stopping potential. And you can see the current reaches a certain value and then it no longer increases or decreases. So it has reached saturation value. It has then become saturated. Why I have drawn two or more lines? It depends on the intensity. This is less intense light. This is less intense light. This is more intense light. More the intensity of light, you will see more current, and that's what we saw before. More light falls, more current will be produced. That's why the graph slightly increases in height. That's all. Okay. Stopping potential is independent of intensity is one important feedback which you should know, because all these graphs eventually end up terminating over here. Irrespective of the intensity, the stopping potential will not change. Keep these things in mind. All these are important key takeaways. Okay. But, this graph, they have also drawn in NCERT in a slightly different manner, but for different frequencies of light. Different frequencies of light. Because the stopping potential actually depends on the frequency of the light as well. So this is how it looks like. This is voltage versus current graph. This is O. For the same intensity of light, let's say the light reaches this saturation over here. Let's say this is minus stopping potential 1. If you take light of a slightly different, if you take light of a different frequency, you will see that the graph will go like this. Saturation will be same. Basically, the intensity is same, but it will have a different stopping potential. It will have a different stopping potential. So this is with light of different frequencies. Light of different frequency, but same intensity. Same intensity. Because if intensity is same, the current will be same. Current will not change. The problem is only with the stopping potentials. So why does this happen? You will get the idea. See, you don't have to memorize this. If you know the formula, you will understand why this happens. The formula is energy of any photon. Energy of any photon is the work function plus the maximum kinetic energy. Now, energy of any photon is HF. Work function is a characteristic of the material. I'll just keep it as it is. Plus EVS. In this formula, you can see it is definitely independent of intensity. Independent of intensity. So stopping potential does not depend on intensity. Stopping potential does not depend on intensity, but it does depend on the frequency. So if somebody increases the frequency of the photon, the stopping potential will also correspondingly increase. Understood, my dear warriors? Let me just put my pad on charge 1 second. Yeah, perfect. I'm so glad, Krishna. Yes. Yeah. This is there in CBSE. Yeah, this is there in CBSE. It's not like